All right. Good morning. I overheard you guys have quite the week. Assignments, homeworks, exams. So sorry to hear that. So was no intent to give you an exam during that. We really don't have time to collude that much, and it might be arguable whether we like try to spread it out or give it all at once. Probably best we don't collude. So there's no no malintent there, right? Okay, so how many of you tuned in on Sunday? A couple of people. It was a long session, so sorry it took so long. But I hope that was helpful. I had a few people accidentally tune in from the other class, not realizing, and they got really confused, thinking their exam was moved. So I cleared it up with them, but I wasn't sure how many. Like after I got a couple emails to that effect, I was like, "Ooh, I wonder how many were from this class versus the other one." Okay, at any rate, that should be posted. It's as a link on Moodle. Probably won't be able to find it just looking on the YouTube page. So go to Moodle to get that link. I also posted the slides from that session as well. Okay, so then during that, I touched on some of the membrane filtration topics that were required for the homework, as I mentioned in an email late last week. And so we're going to talk a little bit about those, go through those. I guess if you were attended on Sunday, then you have a preview. We'll work a problem which is similar to, if not the same as, the one problem we didn't cover in the homework solutions, and then we'll really talk about some of the concepts of membrane fouling and what to do about those. So that's kind of the plan for today. I'm also happy to answer any questions you guys have about the exam on Thursday. I'll note real quick that the formula sheet that you have on Moodle is what will be as the last page of your exam. So you should, or last two pages really. So you should have that. Should be a good study guide in terms of making sure you know what the different parameters mean, how you use them, how they fit into a problem. Okay, so then in terms of membrane filtration, there's a couple ways we can talk about how effective they are. And one would be how effective at removing some solute or maybe some particles, something that you're using the membrane to remove. So on a solute balance, we would talk about it as some fraction rejected, and we'll call that capital R. I'm following some terms here. Our book touches very briefly on membranes. There's not a lot there, so I've also taken from some of the other books I listed on the syllabus, and I'm just trying to keep pretty consistent with the notations there. So we have a capital R for fraction rejected. We'll see in a minute we have a lowercase r for the water balance. So the fraction rejected then is very much like what we've seen in terms of the fraction removed, right? 1 over C over C naught. Whereas just C over C naught would be the fraction remaining. So in that sense, if we have a membrane and we're removing some portion of our contamination, we can take a look at it in a very similar manner where instead of some initial and final, we're looking at feed and permeate, right? So it's very similar in that sense. So if we have C in the permeate, C for the feed, and maybe we have some C for retentate. So in that sense, our fraction removed is fairly directly connected to that previous concept. This is 1 minus the concentration in the permeate divided by the concentration in the feed. Okay, so if those are milligrams per liter, then we see, that would be a typical scenario. We could have some portion removed. And we can also put that in a log form. So we could say log base 10. So our log would be the log of the CF divided by CP. So this is a bit of a rearrangement. So our log is talking about, that's the conversion between, the way of writing it where we'd say 1 minus 0.0001 remaining. That's a little cumbersome to say 99.999% or whatever. So instead of doing that, we can take the log of the CF, concentration in the feed, divided by the C in the permeate, concentration making it through the membrane, and reporting that as like a 2 log performance or 3 log reduction kind of thing. So if we take a look, this should make some sense. We have an example here. If the fraction rejected is 1 minus, let's say 1 over 10,000, we get 0.9999. And to express that as an R log, we would say the log of 10,000 divided by 1 is 4. So that gives us a pretty simple way to say the same thing without all the 0.99999 stuff. Okay, so that's essentially the basics for the solute balance of something. And we notice, in this scenario, the CR is not too relevant if we're just talking about the performance. Now, we should be able to do a mass balance. So a note here that, just to make it very clear, for a membrane system, we generally don't see it as accumulating meaningful amounts of our solute. Yes, we will have fouling, but if we were to do a mass balance, we're not going to notice that substantially in terms of, are we accumulating stuff? It's just not on a time scale that will really affect the flows, the amount leaving rejected or permeating on a mass balance type of thing. So we'll assume, in that sense, a steady state. And then it's very simple because there's no reaction. So what's going in is going to be equal to what's going out in terms of rates. So that would be CF times, and we could write QF, QR, and QP. So CF QF would be equal to CR QR plus CP QP. So that should be obvious once you take a look. We're just sending some things into this box and it's coming out in 2 different directions. We happen to be changing the concentration, but the overall mass, is conserved. So that should be pretty straightforward. And that means that if we do have something known about the solute balance, this fraction rejected, and we have some knowledge about the flows, then we can solve for any piece of that puzzle, right? We can have complete control over this mass balance if we have knowledge about the flows and some knowledge about the fraction rejected. So regarding the flows then, we would call it a water recovery rate, lowercase r, and this would be simply how much water are we recovering through the membrane. We say recover, produce. We are feeding the membrane a lot of water. How much of that do we actually recover as usable is kind of the terminology there. And this is the QP, again, what makes it past that membrane, versus what we're adding to it to filter. So again, we have a system where we're not really talking too much about QR, the rejected stream, but inherently we will see, again, from the mass balance, or I guess just a water balance, QF is going to be equal to QP plus QR, right? We're not going to create or destroy any water inside the membrane. So given some water recovery rate, just the ratio that we get out, so if the water recovery rate is 0.5, then we're achieving 50% of the water we give to the membrane comes out as clean water, and the other 50% goes away. So with that, we can really characterize our whole system. Okay, so then if we had an example where we were treating 100 liters of water, 15% of it goes to waste, R should be 0.85 because 85% of it was going to, permeating through and acting as produced water. All right, good so far? So these were concepts, like I mentioned to you, we had not covered yet, but if you were able to take a look at the equations and these slides I had posted for you, these ones hopefully were pretty straightforward, and you could have at least seen how they were going to apply in the problems. Okay, so I have a problem here, and this is seemingly way out of, I think I hit end instead of next, sorry. Okay. Skipped to the last slide. All right, so flux. We've talked about it. We've talked about flux in a few senses, in part in granular filtration and in part in the first section of membranes. So just want to be clear and then add a bit here today. So flux will be the, we would call it J, and this will be flux across the membrane. So if we do have a membrane, then what we're really talking about is not the Q that's reaching it, the QF here, but the flow that's coming through, the QP, because we might have some QR. So we're going to say the flux that makes its way across the membrane is how we're defining it. So it'll be QP divided by the area of the membrane. So that's one aspect of the flux that we're going to talk about. And the next things we're going to do is really relate this to how we might be able to understand the pressure requirements given a particular membrane type or given a particular fouling situation. We did have a problem. We briefly touched on that in the homework as well. But first, we have this problem that was pretty close to the same as on your homework, so I want to talk about it here. This is actually an example of a problem from one of those alternate books. We have a membrane module containing 5,760 fibers. The fibers are 1.87 meters long, with an outside diameter of 1.3 millimeters and an inside diameter of 0.7. So the task is to calculate the water production from one module if the flux is 75 liters per square meter per hour, and the direction is either 1, outside in, or 2, inside out. And it asks us to compare those answers. So what we're really dealing with here is a membrane that has a lot of these hollow fibers in it. And I'll draw this a little bigger. I mentioned this in class last time, but we can consider that if we were to zoom in on one of these, it would look something like this, where we have either a separation layer on the inside, or if we operate from outside in, then the separation, we would consider the separation layer to be on the outside edge. So we can take a look at either the inner diameter to give us the surface area or the outer diameter to give us the surface area. So in one case it was 0.7, millimeters, and in the other 1.3. So we're going to solve this essentially twice, get the two different answers here, and take a look. In addition, we also know that the length was 1.87 meters. So in one module, we have 5,760 of the fibers. So part of the question here is, what is the area? So we'll do 1, and we probably won't need as much room to go back and do number 2. So the first thing I would say is the area of the membrane is what for a given module? Because the water production rate, so let's calculate the water production from one module. I would say that's QP for one module. That's sort of what we're after. So to get there, we're going to want to look back on our flux a moment ago, right? QP, we can say, is equal to the flux times the area. We were given a flux, so we need to solve that area of the membrane in one module, right? So in this case, the area we should be able to get if we can find the circumference and the surface area then of the membrane. And just to elaborate a little bit onto this, in the inside to out, water's flowing here and then making its way out. For the outside in, the water's flowing from the outside and heading in. So those are the reasons. Whichever operation we're taking, the water's meeting either the outside or the inside first, and that we'll say is a separation layer. Okay, so number 1 says outside in, so that means the diameter we're going to use is going to be 1.3 millimeters, or 1.3 times 10 to the minus third meters. So the area should be 2 pi r times the length, right? That'll give us the circumference of the circle, and then multiply it by the length of the system. So that's the area for one fiber. So the area for one fiber would be 2 pi r would be pi times diameter times the length. So we could say that is pi times 1.3 times 10 to the minus third meters times 1.87 meters. So the area of the module then would be pi times diameter times length times 5,670. Excuse me, 760. Okay. So we'll go ahead and pull up Excel to do this calculation real quick. All right, so we have area of a fiber. We'll go ahead and say that's equal to, well, we'll do this. Okay, so area of one fiber there, area of one module would be equal to this times 5,760. So for one module, we have an area of basically 44 square meters. Or possibly just under. Okay, so that means we now have our flux, we have an area, so the Q should be, and let's check the units here, we have the flux in liters per square meter per hour, so we could say 75 liters per square meter times hours times 44 square meters. So we can get that in a liters per hour value. And that would just simply be that 44 times 75. Oops. So that should leave us in units of liters per hour. That would be really just about 3,300. Okay, it's not asking for any particular units, so I'll just go ahead and leave it like that. And for part 2, it's basically the same thing, but this time our diameter is going to be 7 times 10 to the minus 4 meters, so 0.7 millimeters. And then we do the same calculations. So the area of the module, if we do all that the same, what am I doing? We'll just repeat this and say, just update this to be 7 times 10 to the minus 4. So our area of the module should be 26.69 there. That means our QP came out to be 1776 or 77 liters per hour. Okay, so we have those two values then, and we are asked to compare them. And I guess the simplest way to do that would be to say, if this is outside in OI and this is IO, we could just say Q, we could do IO over Q, OI over IO, just to compare how much more is one compared to the other. Would be a simple way to compare them. So we'll just say the 3,300 divided by the 1777. So one is 1.87 times more than the other. So 1.885. So we could say that's, 86% more than the other, or we could invert that, do the exact inverse and say, well, the smaller one, doing inside out gives us 53% as much water. Whatever way we want to compare those would work out all right. Just make some sort of comparison. So it's really almost twice the production just by operating it the other way because of the geometry. All right, any questions or issues with that? Okay. So on to pressure then. Speaking of a difficult week. So the transmembrane pressure, TMP, I think we mentioned, this is what we will take a look at to see how are we pushing the water across our membrane. So we'll define this in pascals. So transmembrane pressure, really what we're talking about is if we were to measure the pressure, if this is some sort of membrane, if we measure the pressure in the feed being applied to the membrane and then measure the pressure as it's coming away in the permeate, we should expect some pressure drop. And that should make sense if you think about, if you've ever used a syringe filter, you're applying a lot of pressure with your thumb, trying to get the solution through. And when it comes out, it has a little bit of pressure. Now, if you're really squeezing on it and the membrane itself is letting a fair amount of water through, you'll see it could, you could squirt water. It would have some pressure based on the pressure you're applying, but it will have dropped compared to if there was no membrane there at all, right? It would act like, a squirt gun sort of a thing, or a pool toy that, shoots water out, except that the filter is dropping that pressure. So across that membrane, we have a pressure drop that's expected. So anytime we have a flow, we expect that there will be a pressure differential that is driving the water. So it's really that difference that is the force we can use to push water through. Okay, so then to relate this to our actual flux, we can define flux as, we've defined it already as the flow that happens to be going over some area, but now we can also say that it's going to be equal to this pressure applied divided by the resistance that the membrane is providing times the dynamic viscosity of water. So this will be the transmembrane pressure divided by some total membrane resistance times the viscosity. And you could think about it, if you were to try to push honey through a syringe filter, just imagining that, you can tell that would be more difficult, right, than to push water. So the dynamic viscosity of water, or whatever fluid you're going to filter, will matter here. This total membrane resistance is going to be in per meter units. It's kind of like it feels a little bit like a first order rate constant. Some portion of this stuff happens over some time. Some resistance happens per distance you're filtering it through. So it's sort of like a portional unit there. And this membrane resistance, since it is in per meter units, it tends to be a very large unit. So it's like, 1 times 10 to the 11th resistance per meter. But fortunately, instead of filtering through 1 meter, we're trying to get it down to like a really, really thin layer, right? And so it looks like a very large number. It acts like a very large number because we're working in meters. But if we were to work in micrometers, it wouldn't be such a big number. Okay, so let's take a look at what these membranes actually might look like. And perhaps I should have started here, but when I was talking about last time the support layers, the different membranes, and whether or not you could like squash them, this is the type of thing that I'm referring to is in a given membrane here, you'll see that there are these large channels, large spaces. Those would be the support layer. They're large pores. They're effectively trying not to impede any flow. That's trying to let as much water through as possible while providing the pillars or foundation or supporting structure to hold up the selection layer. So really the membrane layer itself. So up here we see that it all comes to a bit of a point, and we actually can't even see the pores directly because they're pretty small in this micrograph. So that would be the selection layer, we would call it. Or the separation layer. So when we design a membrane, typically we will try to have that one component be very thin and be supported by a wider structure that's not going to add any resistance meaningfully. And so then our resistance is all coming from that thin layer there. Of course, if we have fouling, let's imagine over here, this is our membrane, and these are particles being stuck and loaded and fouled on top of the membrane, then we actually end up with a scenario we'll talk about where if this is all foulants, we might be filtering through the foulants, and we would end up calling that essentially cake filtration, where we are, or like a cake layer foulings, where we are filtering through all that stuff that has been added onto the surface. That will improve our performance in the terms of like what can we reject and how much of it are we rejecting. We'll reject smaller stuff because of the fouling, but that's going to decrease our performance in terms of the flux, the pressure requirements, all of that. Okay, so we can see a few, so a cake layer filtration is what I meant to say. All right, so we can see a few more examples here. There's wider pores, and in this sense, you can kind of see the little channels through here. That would be the separation layer and the support layer. There is a wide variety of ways to actually generate or produce these membranes. And so depending on what material you're using, depending on what pore size you're aiming for, there really can be a lot of different ways these would appear. This one down here looks very, very much like it's tight pores, very flat surface, and then a spongy-like pore system to support it that is clearly larger pores than whatever is on that separation layer. Okay, so then when we consider resistance and what adds to the resistance, we can define three different components. One would be the resistance due to the membrane itself. If the membrane was clean, nothing has happened to it yet, it's just the membrane, no other feature happening, that would be our RM. So if we have, let's say, a pore structure, a separation layer that's kind of right at the surface, that has these smaller pores. Try to draw it a little better. So kind of like what we saw a moment ago, I'm just going to use a little bit of this space. Larger pores where water can travel through. This RM is coming from the membrane itself, right? Just the portion that is the actual membrane. Now, we could then take a look and say, well, what about the fouling resistance? Our fouling can take form in a couple ways. And I will say that, I'm going to use part of this. Our fouling can clog the surface, can clog the pores, can get mixed up inside of here to some extent, and can just narrow the pores by these particles getting stuck along the way. Okay, so that's our typical fouling. What that would look like would be resistance due to fouling of the membrane generically. And then we're going to have a separate cake layer resistance, which is also fouling, but we're going to make a distinction here to say that really that is, that's what happens if you have the cake layer, the fouling gets so bad that you end up forming an entirely new layer of filtration like we saw in the previous slide. And so as we build up sort of a quasi-fouling membrane and water is traveling through that, that becomes our cake layer resistance. Of course, the membrane itself would also be, behind here and all that. So I was just trying to kind of distinguish those pieces there. Okay, so all this to say is that membrane cleaning, having some way to remove the fouling, is going to be pretty important to keep our resistance lower. So we'll design a membrane. There's going to be some inherent resistance to flow. That's what we expect. That's why treating seawater to remove salt is going to take more pressure than treating a nice clean surface water to remove a few large particles, right? There's going to be a big pressure difference right there. That's coming again from our pressure requirement. It has to do with the total resistance here. To get some value of flux, we have to overcome that resistance, and that resistance will be inherent in the membrane plus whatever's fouling. So that means if we can clean the membrane and keep it pretty close to the natural design or the original design, that's going to be either more flux or less pressure. So in either way, we're more efficient with our process. So membrane cleaning then is pretty common and will happen often with a pretty high frequency. Maybe every 30 seconds there's a small backwash pulse, or maybe some agitation physically to help knock off any cake layer. All right, so there's one more concept here to talk about, and that is membrane permeability. And this is just the ratio between the flux and the transmembrane pressure. If we actually go back, we just defined our flux as TMP divided by the membrane resistance times mu. We could see if we're going to define this permeability, it's actually pretty similar, right, to this equation. We could even see that 1 over this total resistance times the dynamic viscosity should actually be the same thing as this membrane permeability. That's just a side note. Don't worry too much about that. I don't think that'll be relevant. If you have both of these equations, the algebra will work out that way as needed, right? But these are our two equations then that we can consider that we have that relate to the flux, the pressure that we're dealing with, and this permeability. You can think of it, you probably have seen something in terms of groundwater. We talk about groundwater with how permeable is it, how resistant to flow is it for water traveling through. And it's a very similar concept here. So we have some permeability that the membrane has, and then we have fouling that can affect it in different ways. And this is just a bit of an elaboration here. We could have the pores of our membrane completely fouled or plugged if the particles happen to be the right size to just plug them up. Standard blocking is kind of what I was trying to draw a little bit, where particles are starting to foul the inner lining of our pores, therefore constricting them. At some point that develops further, and then we get what we might call intermittent blocking or intermediate blocking, fouling, where we're starting to get a bit of a cake layer, but it's not really all the way there. And then eventually we have the cake layer where water literally has to make its way through the pores around through the pores of the cake layer before it can make its way through the pores of the membrane itself. So we would see then the permeability decreases as the resistance increases. Should make sense with that. Okay, so that's about all I have for really the technical aspect of membranes. We now have, I don't know if you've taken it, I think Dr. Christie taught the membranes class last semester. So we now have a potential option to go deeper into membranes. So talk to him if you're interested. I'm not a membrane expert myself. I've worked in two different labs where some membrane research was going on, but I was never a part of the membrane side of it myself directly. So I have some experience, but more tangential. Okay, otherwise, I just have a couple more practice problems, or just one practice problem here, if you'd like to take a look. But I think we've done a fair bit if we include the homework problems. So I'll read through this with you. But how are you guys feeling about about membranes, about the exam, about all that? Feeling all right? Maybe. All right. So let's read through the problem, and I'll give you a few minutes to take a look, and I'll give you some thoughts on what solving it would probably look like. And if you'd like, I can solve it all the way. We have time, or we could let you go early. So, all right. So here we have operators of a small groundwater cleanup decide to implement cross-flow microfiltration membrane unit as a pretreatment step to ensure the influent groundwater does not contain large particles that may clog up the rest of the treatment. The system must treat 200 liters per hour. It utilizes a membrane with a pore size of 2 micrometers. It's pretty large. Must recover at least 95% of the water. The influent water contains 30 milligrams per liter of these particles, and the membrane rejects 85% of them. So first of all, it's asking for us to label it on the diagram. Then part B says, what is the concentration of the particles in the permeate? Part C, what is the concentration of particles in the retentate? And then part D, if the membrane is rated for a flux of 25 liters per square meter per hour, what total membrane area is required? Okay, so this is kind of stuff we've done. You know, we've seen now problems on this type of thing. In this diagram here, A would be our feed. Water is going to flow across the membrane, so then B is the stuff that was rejected, the retentate stream. And D and C are the same. Doesn't matter which one you label. That would be the permeate. All right, so take a minute. I think the problem is pretty straightforward, so we can solve it. Won't take too long. All right, so you see approximately what I've done so far. Had a couple minutes to take a look at it. I went ahead and drew up the pieces, wrote up the flow rates. I'm using a bit of an approximation, so well, we know that QP, the amount we have to treat to permeate through, is 200 liters per hour. That's a little bit, it feels like the problem is probably not worded the best, because for groundwater treatment, we're probably treating a certain amount and all of that amount has to be treated. So membrane, we probably wouldn't actually have much that's rejected. And if so, I guess we'd have to treat that separately or something. So it's a little vague in my mind about this 200 liters, is that the feed or the permeate? But the wording, I think the closest thing to say would be that would be the permeate. That's something you could ask me if it's unclear on an exam, by the way. The supposition, though, is that, since we must treat that amount and we have to recover some percentage of that amount, that should be the permeate. So we're going to treat that as the permeate. That means the Q feed needs to be a little bit more than that. In fact, about 5% more. So if we take 200 divided by 0.95, that's just around 210 liters per hour. That leaves approximately 10 liters per hour for the retentate. So we're just going to go ahead and use those numbers. We know that the concentration of particles in the feed is 30 milligrams per liter. And using that and the portion that's rejected, which is 85% of them are rejected, we can use this equation, 0.85 equals 1 minus Cp over 30. That's Cp over the Cf. We should be able to get a Cp value of 4.5 milligrams per liter. And just thinking about it, this should be reduced compared to what's in the feed. That is true. So that's a good sign. For part C, we are asked what is the particle concentration. So we can set up this mass balance here, QRCR. We can set equal to, so that's what's being rejected is what's equal to what's in the feed minus what's leaving in the permeate. So I'm kind of in the middle of that on my Excel sheet. So we'll get that in just a second. CR. So we'll just take the QF CF minus the QP CP. So 200 times 30 minus this, 210 times 30 minus the 200 times 4.5, and divide all of that by the Q rejected, which is 10. That should give us 540 milligrams per liter. Okay, so then part D says if the membrane is rated for a flux of 25 liters per square meter per hour, what total membrane area is required to meet these demands? All we have to do here is really just say that flux, again, that's going to be the flow across some area. So if our flow rate, and that should be our permeate flow rate, if that has to be 200 liters per hour, then really all we have to do is say, or account for that flux there, and then we'll get our answer. So the area will be equal to this QP divided by the flux. So that should be 200 liters per hour divided by 25 liters per square meter per hour. And if we take 200 divided by 25, that should be 8, right? 8 square meters. Okay. All right. Any questions about this, about the exam? Anything? All right, so that's all I've got for you. I'll see you on Thursday for the exam. It'll be here, same time as normal, and it'll cover everything we've done so far.